Welcome back, everyone. This is the second part of statistical analysis, in which we will be looking at inferential statistics. The very first thing that I'd like to do is to make sure that you all have a clear understanding of the concept inferential statistics. So what are inferential statistics? Inferential statistical techniques use data from a sample to make inferences about the larger population from which the sample was taken. Because the goal of inferential statistics is to draw conclusions from a sample and generalize them to a population, we need to be very sure that our sample is an accurate representation of the population. The aim of inferential statistics is to reach conclusions that extend beyond the immediate sample data. For example, we can use inferential statistics to infer from the sample data how the population might perform on a particular measure. We can also use inferential statistics to evaluate the probability that an observed difference between groups is a real difference or a dependable difference, or whether it occurred by chance, in which case you cannot conclude that your observation is dependable. Thus, you can use descriptive statistics to simply describe your data, but you will have to use inferential statistics to make inferences from your data about the general population. As this is meant to be an introductory course, we cannot discuss all the different types of statistical techniques that are available to researchers working in a quantitative paradigm. We will focus only on the most commonly used techniques in inferential statistics, which include hypothesis tests, confidence intervals, and correlation and regression analysis. We will consider each of these commonly used techniques in turn, and will then turn to the actual statistical tests that are associated with each of these techniques. The first technique that we will consider is hypothesis testing. Hypothesis tests use sample data to answer questions such as, is the population mean greater than or less than a particular value? And are the means of two or more populations different from each other? Let's look at an example. Imagine that you examine the effectiveness of a new Grade 1 literacy intervention program by comparing literacy outcomes in an experimental group and control group. You found that the experimental group performed better than the control group after the intervention. Hypothesis tests can tell you whether the positive effect that you observed is likely to be a real effect that you will also find in the population. You might ask why you need to test this. Well, for the simple reason that we don't want to risk rolling out an intervention to an entire population if it is effective only in our sample. We need evidence that the intervention will be effective in the entire population of Grade 1 learners. Hypothesis tests help us to infer whether we can extend conclusions from our study to the larger population. Note that, in the example above, if the statistical test that you opt for renders a significant result, it suggests that the observed difference is a dependable difference. We can then say that there is a significant difference between the means of the two groups. Another way of explaining this is to say that the difference did not occur by chance. Let's turn to confidence intervals. A primary goal of inferential statistics is to estimate population parameters. These parameters are the unknown values for the entire population, such as the population mean and standard deviation. Population parameters are almost always unknown, as it is typically impossible to include the entire population in any study. Let's look at another example. Suppose the population you want to study is Grade 8 English First Additional Language learners in South Africa. You can draw a random sample from this population and then establish that the mean obtained on a reading comprehension test is 40% in your sample. Your sample mean of 40% is an estimate of the mean performance in reading comprehension in the entire population. However, it's almost certain that your estimate of this population parameter is not exactly correct. Confidence intervals incorporate this uncertainty to create a range of values the actual population value is likely to fall within. For our example, a confidence interval of 3644 indicates that we can be confident that the real population mean for reading comprehension in grade 8 learners falls within this range. The final common statistical technique that we will consider is correlation and regression analysis. Correlation and regression analyses describe the relationship between an independent variable or a set of independent variables and a dependent variable. Recall the example we used when we spoke about research design. We looked at the design we would need if we want to study the relationship between test anxiety, which would be the independent variable, and test performance, which would be the dependent variable. Imagine that the fitted line graph to the left, which is based on a scatter plot, displays the relationship between test anxiety and test performance in your sample. The data suggests that when anxiety is high, test performance is low. Correlation and regression inferential statistics help us to determine whether observed relationships like these also exist in the larger population, and that it didn't just occur by chance in our sample. You have to decide which statistical technique or combination of techniques will allow you to answer your research question. Once you have decided which technique you want to use, you have to choose the statistical tests that will yield the inferential statistics that you need to answer your research question. This choice of test is partly determined by the nature of your data. The distinction between parametric and non-parametric statistical tests is important here. A parametric test is a hypothesis test which provides generalizations for making statements about the mean of the entire population. Such tests rest on various underlying assumptions, such as that the variable under study is normally distributed in the population and in any subgroups in the population. A non-parametric test, on the other hand, is defined as a hypothesis test which is not based on underlying assumptions. In other words, it does not require the population's distribution to be denoted by specific parameters. Such tests are based on differences in medians, not means. When using parametric tests, you always have to check whether your data meet the underlying assumptions that the tests rely on. I don't want to go into too much detail here, as I will include a reference to the underlying assumptions of each parametric test when I explain that test. Typically though, when you want to use a parametric test, the test assumes that your data is normally distributed, that there is equal variance amongst groups, that there is no multicollinearity between variables, and so on. If you do want to read more about assumptions before you continue with the rest of the slides, you can have a quick look at this source on common assumptions in statistics. Note that for each assumption that you have to test, there is also a test. These tests are not inferential tests, but tell you whether it is okay to apply a particular test to your data, given the distribution of values in your data set. For instance, the assumption of normality, whether your data is normally distributed or not, is tested by the Kolmogorov-Smirnov test or the Shapiro-Wilk test. Unlike an inferential statistical test, you do not want the result of an assumption test to be significant. A significant result on the Shapiro-Wilk test means that your data failed the assumption that your data comes from a normal distribution. What should you do if assumptions are violated? You can try to do corrections by removing outliers from your data set, by removing missing data from your data set, or by transforming means. If none of these corrections improve the violation of an assumption, you need to opt to do a non-parametric test. You can sometimes continue with the analysis using a parametric test if the statistical test is robust and if your sample size is adequate. For some parametric tests, the result will be relatively reliable even when assumptions are violated.